Okay, so we start chapter 5 today. Chapter 5 is short. There's only 3 sections. Then we review and we test on it right away. Okay, so basically 3 class periods and then a test. What we're looking at in chapter 5 is different properties of things in triangles. And the very first one we deal with is if I look at a triangle, like the one that's drawn up on the board or one that I have here in my hands, if I fold the top down and the sides in, what does it create? Shape. Not quite a square, a rectangle. So if you know some things about rectangles, right? So if this makes a rectangle, what do you know about LN, which is this top portion of the rectangle, and AB? You know about LN in the bottom of the rectangle? Yeah. LN is half the size because LN in the bottom of the rectangle are the same, but when I open that up, the bottom of the rectangle is 2 of the LNs. So we go bottom of the rectangle and then out to A and B, that's double it, right? So LN is half. So I'm going to skip to number 3 and go there. And say that LN is half AB. Absolutely. What else would I know about those 2 lines? What relationship could they have to each other? Do they ever touch? So what are they? Say it again. Parallel. Nice. All right, what about CL? The top going from that LN up to the point, and LA. So here and here. Can you tell me about those 2 pieces? Yeah. They are congruent. How about CN and NB? Other side. Yep. Also congruent. Which makes, if CN is equal to NB and CL and LA are equal, makes L a what for CA? Midpoint. And N? Also a midpoint? Okay, so a mid-segment is a segment connecting the midpoints of 2 sides. So we connect the midpoints of 2 sides, we get a mid-segment. And our mid-segment theorem basically just says what we just figured out just looking at that triangle and folding it into a rectangle. If a segment joins the midpoints of 2 sides of a triangle, like LN did, then that segment is parallel to the 3rd side and is half its length, which is exactly what we discovered in 2 and 3 when we just thought about the fact that if I fold this into a rectangle, I've got those equal parts in those rectangle relationships. Okay, so what we do then is we use that mid-segment theorem. So looking at that picture, E and B are called what for each side? Midpoints, I heard. Absolutely. And you can tell that how? How do we know those are midpoints? Perfect. Because both of the parts of that segment on top and on bottom of point E are congruent. AE is congruent to EB, E is a midpoint. AB is congruent to BC, B is a midpoint. Which makes segment EB a mid-segment. Nice. As soon as we know it's a mid-segment then, we have two properties where the mid-segment is half of the base and parallel to the base. So first of all, how long does BC have to be? 10. How do you know it's 10? Because AB is 10. Absolutely. You got equal tick marks there. We know it's midpoint. So the side parts of it have to be equal. How about segment EB then, the mid segment? How long does this segment have to be? Say again. Why does it have to be 9? Very nice. So whenever you're looking at these mid segments, one, you got to check to make sure you have midpoints. But two, figure out which one it's parallel to, and it's going to go half of that to get to the mid segment. Mid segment's always the smaller one. It's got to be, because it's in the middle of the triangle versus the bottom of the triangle. It's got to be smaller. Which should help us on this next one, where we have H, J, and K are all midpoints, which tells me HJ is a what? If H and J are midpoints. Mid-segment, absolutely. So is JK, so is HK. So we have 3 mid-segments in the middle there. I want to know how long JK is. So what is JK parallel to? Which side of the big triangle? EF. So then, how do we get JK's length? 60 divided by 2. So JK is 30. All right, then I want HJ. Think about what HJ is parallel to. Which one? 100, absolutely. So how do I get HJ's length? Divide by 2. Just like normal, something like taking half of 100, I'm not going to expect to see work on it. I'm writing it here, so if you go back and look at your notes, it's not, well, she just wrote down 100. I don't have any clue how she got 100. It's, I'm showing you I got 100 because I'm sorry, 50 because I took half of the 100. So my notes off to the side are not something you would be expected to do on a test. You would just give me whatever the half value is. But they're there for you to help you if you use these to review. All right, then I need FG. Well, FG, though, is part of the big triangle. So what should I look for? The parallel line. It's the same process, but now I have the littler one. I have the mid segment. How do I get the big one? Multiply by 2. So FG is? Questions? Okay, so main goal there is figure out what one it's parallel to. And then if you're looking at the big one is what you have, you take half. If you've got the small one, you double. Mid segment gets doubled. Side of the triangle gets halved. We good? Okay. So on the back side, we got Dean swimming the length of a lake and wants to know the distance he swam. So we got a whole big situation here. He paces 35 from the edge of the lake and sets a stake. So here he is, starting in the bottom left corner. He paces 35 paces and then sets a stake. Then he keeps going, and he paces another 35 and places that stake. Now he walks to the other side of the lake. So he goes all the way from that top point down to the lake. And that is 236 strides. Then he paces back half the distance. Well, if he goes back half the distance, how many paces did he go? Half of 236. Perfect. And from there, when he places the stake, then he paces back to the first segment, or sorry, first stake, 128 strides. What is that last pacing back to the first segment? What is that for the triangle? A mid-segment. How do you know it's a mid-segment? because we've got two sides that are cut into congruent parts. Absolutely. We got 35 and 35. So those two are equal. If he paced back half the way, you know if that one's 118, that one's also got to be 118 because that's the other half. So we have midpoint, so we have a mid-segment. So then how many strides is it across the lake? Why 236? Okay. We're going to use a different number. Yeah. Why is it 256? Absolutely. You have the mid-segment. You got to double it to get to the base. Is that okay? So then what if each stride was 3 feet? How much or how far did he swim across the lake? What would you do? Yeah. How did you get 768? Absolutely. So you had 256 strides. You know each one's 3 feet. And so you get 768. And what do we put for a label on that? Perfect. Because of the 3 feet. So for every one stride that he takes, he swam 3 feet, essentially. And so we're just taking that 256 in strides and doubling it. Is that good? Okay, so we can't leave it with just numbers. Sometimes we got to throw algebra in it. First thing to check is, do we have a mid-segment? See nods. All right, what can I do? Do I just set those two things equal? Good. I'm glad I'm seeing shakes. I can't just set them equal because your mid-segment should not be the exact same length as the base of your triangle because you don't have a triangle then, right? If it's exactly the same in the middle of the triangle as on the bottom, it's not a triangle. It's a rectangle. Okay, so we got to do something here. What should we do? Yeah. Very nice. We got to take our mid-segment times 2 to get the base. So just like you would have looked at the 6 and told me the bottom was 12, we got to make sure we use that in the equation because the 6 times the 2 gets me to how long that bottom is. All right, so what's x? One more time. 14. Thank you. You know, it's what somebody over here said. I just couldn't hear it. Questions? Okay. Go ahead and take a look at the next one and see if you can decide what kind of triangle it is from our types of triangles. Go ahead and talk to somebody near you on it. I heard some good words out there. What kind of triangle do we have going on here? Isosceles. Nice. How do you know it's isosceles? Nice. Isosceles needs to have at least 2 congruent sides, and this one does because those tick marks on the left and on the right, it's only 1 tick mark for each. So we know all 4 of those pieces are equal. All right. How does that help me, knowing that it's isosceles? What else can I add to my picture? Because the 6 and the x don't relate to each other, right? They're not parallel. 6 is touching the x. So what can I do to get at x? Yeah. We're mixing a couple processes there. First of all, why did you want to take 6 times 2? Okay, so 6 is my mid-segment. 6 times 2 gives me 12 is the base. That's the length of the base. When you were talking about subtracting from 180, you're talking angles. But we do need to go to angles as well. What angles do we know because it's isosceles? Base angles are what? How do I know the base angles? Because they're congruent. Perfect. You know base angles of an isosceles triangle have to be the same, which makes that one equal. So those two are both 60, which leaves you what for that vertex angle? 60. Okay, so since all our angles are congruent, we know that that is actually an equiangular triangle. But what do we know about equiangular triangles? They're also what? Equilateral. Nice. Why did I lead you in that big circle? How does that help me get x? X is 12. Why? So the base is 12. All your sides are equal. Is what equilateral means. So since all the sides are equal, x also has to be 12. So it's a really long process for what you probably looked at and went, well, I know the bottom's 12. But you have to recognize the isosceles triangle to get that we have base angles the same. If the base angles are the same, then the vertex is also 60 because that adds up to 180, which makes it equilateral. So now I do know x as well. Is that okay? Now, if I'm writing that in my notes and all I write down is x equals 12, do I know how to get that when I'm looking at them later for my homework? No. So I would write some extra notes there. I kind of walked you through the thinking and wrote some bits and pieces down. Write something down to help yourself be able to use this. Because the notes are not just about what we do in here. Yeah, I walk you through stuff in here. But if you don't have the ability to go back and look at those notes and actually understand what we did, the notes aren't helpful to you later. And the goal is the problems I do on the notes are ones that you can use to help you do the homework. All right, looks like most people are done. So what do we want to do on this next one? Variable choice, what do we want to solve for? X, okay. So I see that x is here, here, and here. Which two can I use together? There's 3 different segments that all have an x in them. Yeah. So it's 3x minus 6 and the one that's only x. Why do I want this 2x plus 1? Not parallel. Nice. So I'm picking the two that are parallel. Go ahead and write down an equation right now that you think we should use to solve. Once you have that, check with somebody else just to make sure we all got the same equation. Think about what you have to do to the mid-segment to get to the base. All right, I'm seeing some issues out there. Some are good, some have issues. What do we have to do to the mid-segment to get to the base? Multiply by 2. What if I want to go from the base to the mid-segment? Divide by 2. Is 3x minus 6 easy to take half of? No, because 3 is not an easy number to take half of, right? So let's take the mid-segment times 2, because the mid-segment is x, to get to the base, and the base is the one it's parallel to, 3x minus 6. So I definitely saw some out there where people had them equal to each other. Remember, if they're equal, it'd be a rectangle. That mid-segment is halfway through the triangle. It's got to be smaller than the base. So in this case, we got to double it to get to the base. What happens now? What do we get when we solve that? Say it again. X equals 6. What'd you do first? Subtract the 3x. Now back in algebra, they probably told you you don't want to subtract the bigger x, you want to subtract the smaller x, right? Why would I not bother taking that step right here? They'd both be negatives and they're going to end up going away. Okay? If you move the 2x over to the other side, you get 0 equals the 1x minus 6, and you still have to move another number. So no matter what, you're going to have extra steps. It's just what extra step do you want to have? You can move the bigger x if that's going to be a faster way of solving. So now when we divide by that negative 1, x is 6. All right, so take a moment now, talk to somebody near you, see what you can figure out for finding y. I'll just do this to see if that helps you a little bit. I got lots of them looking good out there. What do we have to do to y to get to solving for it? Multiply it by 2 because it is the mid-segment. But when I multiply by 2, what is it equal to? What's that y parallel to? But there's still two variables in there. Plug the 6 in for x. Very nice. So if 2y equals 2 times 6 plus 1, what does y end up being? 6.5. Questions? All right, we're going to continue using that mid-segment theorem on this next one on our kite design. Just going to hold a second to make sure everybody's got this one written down. All right, so we have a kite with ribbon at the midpoint. So we know these are all midpoints. So the kite is made up of what kind of segments? Mid-segments. So the diagonals of the kite are 64 and 90. So when we talk diagonals, we talk about corner to corner. So we've got a 64 centimeter diagonal, and we've got from other corner to corner 90 centimeter diagonal. I want to know how much ribbon to use, so I want to know what those mid segments would all add up to. Go ahead and work on that with somebody near you. All right, here's my suggestion for you. Cover up half of the kite. So if you cover up the bottom half of the kite, you should be able to find the mid segment for the top half of the kite, because you know how long that middle diagonal is. Then cover up the left side. You should be able to find the right side, and vice versa. So cover up the bottom, see what you got, go to the top. Then cover up left, go to right. Try it one more time, see what you can get. All right, so if I do cover up the bottom of the triangle, so I'm just going to draw at the top of the triangle right here. I know that this base is 64. How long is the segment? 32. So that's this one is 32. Where is that in this picture? That's right here. Okay, what about the bottom triangle then? I do this. How much is this mid segment? 32 as well. So I know I got both of those are 32. Now let's say that I draw out the left side, and I know this is 90. How much is that mid segment? 45. Okay, when I do the same thing on the other side, cover up the left side, what do I get for the right side's mid segment? Okay, so if we know all of those measures, how much ribbon is needed? And how'd you get 154? Perfect. Say again how much it is? Thank you. 154 centimeters is correct. Why couldn't you just add the 64 and the 90? Yes, as long as you realize why you're doing it. Because you have two segments that are each half of the 64 and two segments that are each half of the 90. So yeah, just add them together. But would it work if I wasn't connecting all four of them with ribbon? No. So the reason it works is because I have two sides that are 45. That's why you could just add the 90 and the 64. There's two of each half being measured in. Good? All right. So we move on with these triangles and we go to the next step, which on the next page is bisectors. So we are going to take that piece of patty paper that I just gave you. And in the upper left area, you are going to trace the segment on your patty paper. So do it in the upper left part of your patty paper because we're going to use this patty paper twice. So you won't want to do it dead center because then you won't have enough room for the other one. So put it up here in the upper left-hand corner, put it over the segment on your paper and trace the segment. You don't have those extra lines on mine that I have. Let me show you one with blank. So I'm taking the upper left-hand corner, I'm placing it over the segment at the top of the page and just tracing that segment on the patty paper. Just copy that segment on. Upper left-hand corner of the patty paper. Just trace that for me. Oops, I put you too close to the edge. Got that segment drawn on their patty paper right now, right? If I want to construct the perpendicular bisector, that means I want to do what to this segment? Cut it in half. What kind of angles do I want to make? 90. What's the easiest way to do that to this segment, knowing that I have this piece of paper in my hands? Fold it where? What do I put? Like just anywhere on the patty paper? So anywhere on the line? So the ends, put your ends on top of end. So right now, take your paper, put end on top of end on your segment. And just kind of crease it up there in that upper left-hand corner. Don't go all the way through the patty paper. Just kind of do that top corner with a fold. So put end of the segment to end of the segment. So when you fold the segment, you should only see that half. Good. You open it up, you should have just the fold up in that upper left-hand corner, right in the center of your segment. We good? All right, so then it says, draw a point on the perpendicular bisector. So anywhere on that fold that you just made, put a dot. I don't care where you put it, just somewhere on the fold you made, place a dot. Doesn't matter where. Everybody got a dot? All right. Once you have that dot, whether it's above or below, doesn't matter. Connect the dot to the ends of your segment. Go from the dot to the end of the segment on the left, from the dot to the end of the segment on the right. Not looking for super perfection, but if you can try to be as straight as possible, that's awesome. So you now should be looking at a what? A triangle. Absolutely. Does everybody have the exact same triangle? No. Okay, so I'm doing multiple experiments here all at the same time. Look at your triangle. I want you to compare the lengths of the two segments you just drew in. So you took from the point on the perpendicular bisector out to the end of the segments. I want to know what you can tell me about those two segments you just drew in on your triangle. You got one person that's the same. And yours are the same. Yours are the same. But everybody had different triangles, right? So what does that tell you about a point on the perpendicular bisector? How far is it from the ends? The same exact distance, which is, so I'm going to write in same here, the perpendicular bisector theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of the segment. Equidistant. Equal distance. Same. And everybody in this room had the same situation, but everybody had a different triangle because you didn't all put your dots in the same spots. So it works no matter what. So what we just did there, instead of doing a formal two-column proof or a paragraph proof, we did a proof by example. We took a whole bunch of different examples, looked at them all and said, okay, everyone in this classroom, we're going to trust that it's true. What is also true is the converse of that. All converse means is we flip our if and our then. If a point's equidistant from the endpoints of the segment, then we know it's on the perpendicular bisector. So it helps us going both ways. If we know it's a perpendicular bisector, now I can say those two are equal. So if I was in a two-column proof, my reason would be, for the equal part is, they were on the perpendicular bisector. I can also, if I find out they're equal, then say, hey, I know this line is a perpendicular bisector. So we can go both directions on that phrase. So I just copy one more time on this screen just so we can see them, because now I'm going to tell you that AN and BN are congruent. What do you know N's location is? If those two segments are equal, what do I know, or where is N located? On the bisector. Perfect. That converse. The converse said if it's equidistant from the endpoints, N is the same distance from A as it is from B, then we know it's on the perpendicular bisector. All right, different situation. If I know that line MP is the perpendicular bisector, what can you tell me about AN and NB? What do I know about those two segments? They're congruent. Perfect. And if I know that those two are congruent, what could you tell me about triangle ABN? I don't think it's equilateral. You're close, though. Okay, it's isosceles because we have two congruent sides. We don't know for sure about the third side, so we can't say equilateral, but at least two congruent sides we know is isosceles. Good? All right, so you are going to try that next part with a partner here. We've got line CD is the perpendicular bisector of segment AB. You're going to find CA and DB. Go. Use the rule we just talked about. What's a perpendicular bisector? So any point on it is an equal distance from the ends of the segment. If it helps, trace from the point on the perpendicular bisector to the ends of the segment and do that. You should have two lines traced. So pick one of those points, D or C, draw from that point to the end of the segment. You'll find out which one it's equal to. I think we're pretty good. Lots of people got some answers out there for me. If C is on the perpendicular bisector, I know C is an equal distance from the endpoints of A and B, right? So what's my other segment besides CB that's from C? AC, so how long is AC? 5. And then I can do the same thing from D. D to A is 6. What else is 6? D to B. So you had to look at what's the same from that same point in order to do that. Are we good? Okay. So bottom of the page, it says distance from a point to a line, and we want to pick the shortest distance. On your paper right now, draw the shortest segment going from that point right here to that line. Draw the shortest possible distance on your paper. Some of you need to stop and think. Shortest possible distance. Now turn and look at somebody else's paper. All right, so if I draw out here, is that my shortest? No. Okay. Go over here. Okay. Well, where do you want me to draw then? Because those seem like to make sense. Straight down, making what kind of angle? Nice. We wanted the shortest possible distance. The shortest possible distance isn't the isosceles triangle sides. It's going just straight down to the line because you don't want to make it very long. But it's got to make that right angle. And you're probably asking, why is this anything? Why are we doing this? That's because on the next side, we're going to do a little tracing again. So if you flip over to the next side, you were going to take that patty paper, and in the chunk that you didn't draw on, so the bottom right-hand corner, you were going to trace the angle at the top of your paper. So trace that angle up at the top. So you should now have an angle kind of in the bottom left-hand corner of your patty paper. All right, we are going to take that paper and construct the angle bisector. What do you think I need to do to make an angle bisector when I'm folding? Not necessarily the arrows, because if I put the arrows together, I don't think I go through the vertex of my angle. Fold at the vertex so the lines are on top of each other. So this is the toughest part of this one. You kind of got to pinch the vertex so that your paper will bend. Then you're looking to make the sides of your angle line up on each other. Not the arrows, but the sides. So the actual segments need to line up on each other. So it helps if you kind of pinch the vertex just a little bit so your patty paper starts bending. Then you can kind of move it around, slide it up and down until those lines end up on top of each other. So pinch at the vertex so your paper kind of bends. Then you want to slide until the lines end up on top of each other. All right, so where you folded is your angle bisector. You see how you cut the angle into two equal angles? Put a point somewhere on this angle bisector inside the angle. Don't go to the left of the vertex. Go somewhere on that angle bisector, pick a point. Doesn't matter where. So I put mine kind of out here in the middle. Now you want to draw a segment from that point to each of the sides, but we want it to be the shortest segment. So you're kind of freehanding and eyeballing it. You want to go straight to make a right angle. So go from the point to the side of the triangle, trying to make a right angle with the side of the triangle. Then turn it so you can do the same thing to the other side of the triangle. So we're drawing a segment from that point perpendicular to the side of the triangle. So you're going to end up with those two like I have drawn up here. Go from your point perpendicular to the side. It's not going to be perfect, I get that, but it should be pretty close. You should be able to kind of eyeball if that line from the point and the side of the triangle are perpendicular. We have it. If you wanted perfection, you could use a corner of a piece of paper to help you do it. That helps you make a right angle. If you fold that back together, what do you notice about those two segments you just drew? They're what? They are congruent. Nice work. Now, look at the people around you. See if they put their points in exactly the same spot you put your point. Is everybody's identical? I'm getting some no's. There's some people that are pretty close to the same, but there's some that aren't the same, right? So again, what do we know? Since a bunch of us had different drawings, but we got the same results, that's a proof. It's just a proof by example versus a two-column proof. But what we know is now that point that's on the angle bisector is equidistant from the sides of the triangle. What's equidistant mean? Equal distance. So I want to freehand this in here. We did this. We know these two are equal, because that point that's on there is an equal distance. Vice versa, the converse. If a point's in the interior of the angle that's equidistant from the sides, then we know it's an angle bisector. So it's, do I know it's an angle bisector so I can say these are equal? Or do I know these are equal so now I can call it an angle bisector? That's the two different theorems, the idea behind them. So we should be able to use those in this next part. If I'm given that angle ABL is congruent to LBC, what are the vertex of those two angles? B. So AL, when I trace that, I put the arc at the vertex. Angle ABL is congruent to LBC. Again, B is the vertex. If those two angles are congruent, what can you tell me about AL and CL? They're congruent. Why? What having those angles congruent tells me that BL is a what? Angle bisector. They're congruent because BL is the angle bisector. If I know that AL is congruent to CL, what can you tell me about ray BL? Now that L is an equal distance from the sides. It's sector. And if I know that ray BL is an angle bisector, what can you tell me about angle ABL and angle LBC? This one and this one. They are congruent. Very nice. Yes. Number one or number two? Number two. I'm giving you, that's like the given of my proof. I'm telling you those two pieces are equal, and I'm asking you to tell me what you can conclude off of that. So since I know those two are equal, then I conclude it's an angle bisector. So I'm kind of illustrating both theorems. The first one, we had the angle bisector, so we knew those pieces were equal. The second one, we had the pieces were equal, so we could call it an angle bisector. Good? All right. So then we should be able to do something with this. I want to know the length of FD. Thoughts? How can we attack this? Yeah. Why would 5x equal 2x plus 24? Why are those lines congruent? There we go. If the angle's bisected, you know that it is any point on that angle bisector is an equal distance from the bisector itself. Okay, so if 5x equals 2x plus 4, what do I do next? So we get, so x is, am I done? I heard a yep, and I heard a no. We got to plug it into the equation because what did the question ask for? The length of FD. So when I put things like that on here, I'm doing it because when you think about your standardized tests that you have to take, ACTs for juniors, the Aspire test for sophomores, college entrance exams for seniors, all of those kind of tests will have questions that are multi-step, where you have to find an answer, find 8. But if it's a multiple choice step test, 8 will be one of your answer choices. You have to stop at the end of any question, go back and say, okay, did I answer what it was actually asking? This wanted FD, so what is 2 times 8 plus 24? And I guarantee 40 is another answer in that multiple choice question. Okay, so you've got to make sure that you check to make you answered the right question. Not just a question, because X, what is X is a question, but it's not the right question. The right question is what's FD. So you got to go back and plug it in. Does that make sense? All right, so then what you're going to do is with a partner, you're going to go ahead and do these you-try problems. Once I see people are pretty much done with it, then I will go through, and I'll give you out your homework. Good? All right, working. If you're watching the video right now, please pause the video, do these 4 problems, and then turn it back on for answers. Right, on the first one, we've got a mid-segment at 8, so I have to multiply it times 2 to get to that base. So 8 times 2 is 2x. If 16 is 2x, x is 8. On the next one, we have that dk and kh are equal distance, so that means k is on the angle bisector. If it's on the angle bisector, we know that 2x equals x plus 20. So we subtract the x, we got x equals 20. At that point, it wanted angle DEK. DEK is just the 2x. So 2x equals 40 because I would plug that 20 in. All right, bottom left-hand corner, we either have 2 ways of doing this. Either I have to take the 5x and multiply by 2 to get to my 70, or you could go the other direction. You could take 70 and divide it by 2, which is 35, and say that that's equal to 5x. And either way works, because if I get 10x equals 70, I have x equals 7. If 35 equals 5x, then x equals 7. So either way, you get 7. And then on this last one, you have an angle bisector, so you know any point on VT is an equal distance from the side. T is on VT. So That's it, is on the angle bisector. You've got 5y equals 3y plus 6. Subtract your 3y, we've got 2y equals 6, which makes y 3. And then it wants st and tu, so I got to plug that back in. 5 times 3 gives me st is 15. 3 times 3 is 9, plus 6 is 15 as well. So tu is 15. Homework is worksheet 5-1.